In this video, we're going to go through some of the prescribed steps in setting up a recursive algorithms or recursion. So there's a number of things that we need to take note, and these are the three questions that we need to ask. So let's go through these step by step. In order for us to set up a recursion or using some sort of recursive algorithm to solve a problem, we need to make sure, first of all, the problem is a recursive type. There's a couple of characteristics that we need to look at. And one of them is, can this problem be broken down into pieces such that when the pieces becomes atomic enough, there is a base case of questions that applies to turn a recursion all the way around, right? So everything kind of bubbles back. So there's a base case question. Is there a base case that we can rely on to stop the recursion? We'll get into the specific later on. The second part is a smaller color question. This is in dividing up a big problem, right? Like this. You may have smaller pieces here. So the question is really, can the problem be broken down to smaller pieces? If you can't, do not use recursion. So the idea of recursion is that you have one problem calling another, and every single one of these, f prime, f double prime, f triple prime, these become smaller and smaller. They're basically smaller subsections of these, the big problem. So the original problem is function, right? And then it kind of breaks down into those. So the third question that we need to ask is, can we generalize the steps? Meaning, can these be put into some sort of formula that we could use? If we're to call ourselves, again, in the subsection, right? This calls this, which calls it this, and obviously this calls it this in this sequence. Is the formulation the same in f double prime as in the formulation that we have in the f prime, as in the formulation that we have in f? We'll need to apply these questions as we go through designing recursive algorithms to make sure that these are valuable solving the problem. So let's take a look at each of these questions, specifically the base case questions first. Is there a non-recursive way out of the algorithms, and does the algorithms work correctly for this case? This base case is the termination point. Let's say if you have a factorial problem, if n equals 1 and returns 1, what is 0 factorial? 1, right? So we know in this case it must return. So there needs to be a return path. Otherwise, this recursion is going infinitely many memory consumptions being running out at the end. So the base case occurs when n is at 1 or n is 0. So the answer is yes. Will this ever stop? Yes, when n equals 1, you can't go on anymore, you return it. Can n be negative? No, you can't, right? Because the selection sequence here calls for n being either 0 or else this times this, right? And since n is always bigger or equal to 0, right, as the conditions that we have here, and based on this base case, it's never going to be negative. So this answer is yes. So the next one up, can the smaller color questions be answers within yes? In other words, can this problem be broken down? Every time we call the function recursively, meaning calling itself, right, the recursive call, which in this case is a factorial, would the problem space be smaller? And the answer is yes, because we start up with your input being n, and now it's n minus 1. This thing is going to call factorial n minus 2. And later on, it's going to be n minus 3. And so on and so forth. The answer to smaller questions is yes. Does each recursive call to the algorithms involve a smaller case, right? So this is what we meant by divide and conquer, right? We're solving the problem iteratively through recursion. Iteration is bottom up, recursion is top down. So we're starting from the very top, and then we move our way from n into n minus 1, into n minus 2, all the way until we get to n equals 0, right? So this is from top to bottom. Recursion is top down. Now, iteration starts from n equals 0 all the way up. So iteration is bottom up. This is in direct opposite of a recursion. So the answer to this one is yes. The third one is the most general one, which is the generalizations. Can we assume that the recursive call to the smaller case work correctly? Does the algorithm work correctly for the general case? What does that mean by general case? Assuming that the recursive call is this gives us the value of n minus 1 factorial. So the return statement computes n times that. What we have is this. Just factor this out and just look at this. You know that the solution is this. This is not a hard-coded value, but a generalization in factorial, which is exactly what you're trying to do. So this is that. The definition of a factorial is complete. So the answer is yes. Sometimes you'll have constraints on input argument. Constraint means boundary conditions or the edge cases, meaning n has to be greater than or equal to 0, right? If you don't, then you need to build that. So sometimes we call these things GAR clause. GAR clause is a collection of selection criteria. If n less than 0, then return or something like that. So this is a GAR clause that catches the outliers or the edge cases. You're given a set of constraints to solve a given problem. These constraints are assumed. If they're not given in the case of factorial, then you need to build a guard clause to avoid these solutions from ever getting into an issue, right? Because when you have -1 factorial, that's nothing. You're going to get exception around time. The step for designing recursive solution, this is a summary, what we just talked about, identifying base case, having the exact definition of the problem. Understanding the problem you're trying to solve is definitely number one, right? If you don't understand the problem, you don't know what it is you're solving, you can't proceed with anything. And then you can determine the size of the problem. If n is 1 billion, this is a large number. This is not a good input for a recursion. If you had to recurse that many times, your computer is going to run out of memory, right? Remember, recursion utilizes your stack memory. So every function that is stored on a stack will run out of memory. So you got to determine the size of the problem to make sure that the size of the problem is suitable for a recursive solution. Identify the base case, which is the first question you need to ask, and then the generalizations as well as the breaking down of your problem. If the problem could be expressed non-recursively, you don't want the base case itself to be recursive. You want non-recursive, and this is a selection criteria that has a condition that evaluates true or false. If true, then return. Generalization is also very important. A lot of problems cannot be simulated or emulated using a recursion because they cannot fit the generalization criteria. For example, if you want to traverse through a tree simply has a left and right branches, left, right. You can generalize this problem having a traversal goes through recursion. So that allows you to recurse through every single node inside the tree. There are some problems that could be generalized, some problems you cannot. Having this under your belt ensures that you have a sound, a reasonable recursive solution to solve a given problem efficiently. This completes our discussions on recursive solutioning design.